Good evening, everyone. I would like to welcome everyone in today's session about GAN. I'm sure all of us have heard about the term generative AI. It has created a lot of buzz in the last few years. Uh, so today we are going to discuss one of the generative model known as GAN. It was given by Ian Goodfellow in 2014. It was a major major breakthrough in the field of machine learning. And in order to show that how big a deal it was, I would like to quote some word by Yen LeCun, who is one of the pioneer in this field. This GANs and the variations which are now being proposed is the most interesting idea in the last 10 years in machine learning, in my opinion. Now, before starting up with GAN, I would like to ask Aditya to explain some basic stuff about deep learning.
Thank you, Rohit. Um, yeah, so I hope you can all see the screen. And okay, so before we talk about, um, yeah, so before we talk about GANs or Generative Adversarial Networks, I thought we could have a quick refresher on, deep learning and how, and build up to GANs from there. So what is deep learning? Simply put, deep learning is just a subset of machine learning that is inspired by the biological neural network in our brain. And why is it called deep? Is because we're going to have multiple neural layers in this network, and they're going to work in tandem to create a model and basically train our data. So the job of a deep learning or neural network model is to predict output and recognize patterns using something that we call neural networks. So what are these neural networks? Yeah. So neural networks are basically a collection of nodes or neurons that are connected in a specific manner. And their job is to recognize patterns or predict outputs. And they're connected in, they have certain specific connections, and their job is to recognize patterns. So now, what is a neuron to start off with? A neuron you can think of as a function, right? It takes in a certain input and it gives out a certain output. And the whole aim of this model is that we have some input variables and we have some output variables. So let's take an example. Suppose we want to model whether the price of a house given certain input variables. So what we do is that we take our input variables and we have our output variables, and we want to find some mathematical relationship between them. So if I say that I have x1 as the house size, x2 as the number of bathrooms, x3 as number of floors, I want to predict the house size given these three parameters. Now let's take some dummy formula. Let's say that the house price is equal to a x1 plus b x2 plus c x3. Here the a, b, c, or the parameters in this very simplified formula are what we call weights. So the weights in this neural network are like the knobs that tell how important is each parameter. And what's the whole point of a machine learning model? Is that to find out what these weights are by running different rounds of training. Now, how would we find the value of these weights, right? If that's the whole point of the model. Finding these value of the weights starts with defining something called a loss function. So a loss function tells us how badly the model is doing in terms of with some data that we already know. So if we know that this is what it's supposed to be and it's giving us an output which is very far from that, the loss function tells us how it's doing, and we use this loss function along with certain algorithms called gradient descent backpropagation to sort of help us find out the value of these weights and thus accurately model the relationship between the input and the output. So that's how, in a nutshell, machine learning, especially artificial neural networks work. Okay, now let's talk a bit about GANs. Uh, Very briefly, let's break it up. Right, so GAN stands for Generative Adversarial Network. The generative part talks about the fact that this neural network, the collection of two neural networks, are what is going to be used to generate something. In our case, images. Why is it called adversarial? Because there are two sub-neural networks in a GAN, a discriminator and a generator. So what we're going to do is we're basically going to pit the generator and the discriminator against each other to sort of complement each other, fight with each other, and hence generate our images. Now I'd like to go over to Rohit, who will tell us how GANs are trained.
So what during training of GANs, what we can think is that what we can consider is that generator is a counterfeiter who is trying to make fake money, and a discriminator being the police who is trying to allow only the genuine money and trying to find the fake money. In order to succeed in this game, the counterfeiter has to learn how to make money indistinguishable from the genuine money. And similar concept we will use to train GANs. But before directly jumping into towards the code, I would like to give you a sneak peek from where we will start and what we can achieve at the end of the code. Uh, you can see that initially we just have a random pixels, and I think as few as 100 epochs we can go from this, from left side to right side. Isn't it fascinating, guys? So now I would like to switch over to the code and explain you all the necessary theory along with the code. Yeah. So I will be training the model in Kaggle, because we can find GPUs over here. You guys can create a similar notebook by making a Kaggle account, create a new notebook, and adding the anime face dataset as input. So what I have done is that I have divided the code into three parts. One is the data loading part. Second is the making the architecture of discriminator and generator, and third is the training. First, I will go into how we loaded and how we loaded the dataset into the code, and what kinds of transformation we need to make. First of all, in this block, I have downloaded all the necessaries. I have imported all the necessary libraries which we need, such as NumPy, Pandas, and PyTorch. Fun fact, guys, PyTorch is made by one of our VIT alumni. Uh, in the second block, this data directory has the path where the input images are. In the third block, uh, first of all, I have defined the image size. Uh, we will be generating a 64 by 64 pixel images in the session. Second is the batch size. It defines how many images will be in one batch. Third are the stats. What stats are, when we will normalize our images, the first tuple represents the mean value, and the second tuple represents the normalization, the standard deviation. Train DS is basically we're loading the images with the help of image folder function. It has two parameters: first data directory, and second is transformation. We are applying certain transformation into images. First being resize. We will resizes the input image into 64 by 64. Then we will center crop them. Third is really important, that we will convert the images into a 3D matrix, or we can say a 3D tensor, because at the end we will be applying all the mathematical formulas mathematical procedures onto the matrix in order to generate the images. Third, as we discussed above, we need to normalize as data, and the normalization will be according to the mean and standard deviation given in the stats. Third, we will now what we will do is that the images which are in the image within the training data set, we will convert it as an object of data loader so that it can be converted into batches and into that so that it can be converted into batches and can we can so that it can be become iterable. Third, as after this block, now what we will do is that we need to put like we if we want to train our code model on a GPU. So we need to put all of our training data set and even the model into GPU, and this code exactly does that. I have made over here a class which calls these two above function in order to put the images as well as model on the GPU. So here what I have done is that I have put the training DL which we have defined above over here and put it into GPU with the help of function which I have defined with the help of a class I defined here. After my data set uh, is put into the GPU RAM, now we will move towards the second part of the code which is defining the architecture, for which I would ask Aditya to explain you guys.
Thank you, Rohit. Okay. So now, so far what we've done is that we've taken our dataset, we've pre-processed it, and we've got it ready to train in the model. But before that, let's take a look at what our image type is, right? When we spoke about artificial neural networks, the traditional ones, we discussed how each there are a bunch of layers, and the first layer we're going to have is our input layer, right? And in the housing example, when I said that there were three parameters x1, x2, x3, we just have three nodes in our input layer. In this case, however, as you can see, it's a 64 by 64 image. So does that mean that we're going to have 64 into 64 neurons in our first node? Well, it doesn't. You don't need to be very into ML to know that this is going to be very computationally intensive, and it's going to be very difficult to run this in a normal amount of time, which is what brings us to convolutional neural networks. So this is where convolutional neural networks kick in. They are a type of artificial neural network which is especially designed to handle image data type. So what we want to do is that instead of having a 64 by 64 uh, starting layer of neurons, is there any way we can abstract it, right? Can we start with, a smaller data set and without losing any of the key information? And that's what CNN does. It uses a process called convolution, which helps us achieve this. Feature extraction is one of the prominent features of CNN, right? So let's see how that's done. Suppose our image has is an input of 3 by 3. We're going to use something called a filter or a kernel, which is going to help somehow do some math on this to reduce our 3 by 3 input into a 2 by 2 output, right? As you know, images are represented by a 2 by 2 array of intensities, whether that can be RGB or black and white grayscale. So now what we do is that let's suppose that this kernel is some sort of matrix for now, right? All we're going to do is we're going to multiply each of the corresponding elements and then add them up. So 0 into 0 plus 1 into 1 plus 3 into 2 plus 4 into 3. That gives us 19. Similarly, we slide the kernel from these four to these four and we get the next element and so on. And here's the fun part. In classical ANN, our weights, right? Those parameters that we discussed, they're just scalar numbers like 2, 3, minus 7. Here, the weights that we are going to train to finally model our relationship is this kernel. It is this filter, which is, it could be a 2 by 2 or 3 by 3 array. And what we're trying to do is that we're trying to extract high level features whilst also reducing the size of our input. What do I mean by features? A feature could be anything. So if we're training, say, images of dogs versus cats, features could be the presence of whiskers on the cat or the loopy ears of a dog. The beauty is we don't have to get into that. The machine learning takes care of it through the nodes and the layers. So yeah, the feature extraction happens through these filters, which also serve as our weights in a CNN, and our image size is reduced for processing by picking the integral parts by extracting these features using these weights called kernels. Now, different filters are used to capture different features. So we can have n number of filters based on our particular model. And these filters act as our weights during backpropagation. Now, let's just look at an example. Let's just talk about a few terms regarding these filters, right? So if you can see this filter, it's sort of sliding over and it's reducing our input. So the size of this kernel, the size of our filter here, as you can see, it's 3 by 3. This is called kernel size. Now, after it computes the sum of one pixel in our output, you see it sliding, right? The number of pixels by which it slides towards the right and slides down is called the stride. So here you can see the stride is one. It's just shifting one pixel. And then if you can also see in this example, there's an extra column of zeros that is added to the left and added to the top. This is called padding. Why we do padding sometimes is that we want to take care of something called edge condition. So when the filter comes towards the end, we don't want to abruptly, you know, transmit our output. We want it to be smooth, which is why we do something called padding. So these terminologies will come in later. Great. Now let's look at the code. Okay. So as we discussed that our image is going to be is input is going to start with a 3 into 64 by 64. Why is it 64 by 64? Because that's the height and length and breadth of the image, and 3 because we're going to represent this as a three-dimensional array of red, blue, and green values. Now let's look at this const2d function. The first parameter talks about the number of input channels. We have three input channels in the first layer, R, G, and B. 64 talks about the number of output channels. So how many outputs are we generating? Short note into terminology. This output that we got here is what we call a feature map. Okay, and I'm just going to use this terminology moving forward. The output of every filter. So this is the number of output channels we have, and you'll see in a second why that the number of output channels is the number of feature maps that we're going to generate or the number of filters. Kernel size is simple. This is 3. Stride here is 2, so it's going to move 2 pixels, and padding here is 1, so it's going to pad one uh, row and column about the edges. Okay, cool. So now what's going to happen is that I'm going to explain this for one layer and we can extrapolate it for the others. We take our three matrices, R, G, B. It could be any number of matrices. We can have 10 matrices also. We take one filter, do the operation for each of them, and then add them up. So one filter combined with all the inputs gives us one feature map. And it's okay if you don't get this at the first go. When you visualize it, it will become very clear. And that's why the number of filters gives us the number of feature maps. You can see that now since we have 64 filters applied, we have 64 32 by 32 images. Now why is that? That's because every time you do this, every time you pass it through one layer of convolution, what happens is that the size of the next guys reduces. The extent to which it reduces depends on kernel size, stride, and padding. If you do out the math, you will see that in this setup, it's always going to half. So as you can see, it halves here from 32 by 32 to 16 by 16 to 8 by 8 and finally 4 by 4. Also note that progressively we are increasing the number of filters. Okay, and why we do that? Well, there's a BC GAN paper as to why we put these parameters, which you can check out after. Great. So now, so what we do is we send our input. It gives us feature maps, and before we pass it to the next layer, we do two things. We do one thing called batch normalization, and we do something called an activation function. Without going into too much detail, batch normalization just helps bring some sort of stability to the value, and an activation function is used to introduce what is called non-linearity to the model. Leaky ReLU stands for the leaky rectified linear unit, and ReLU and leaky ReLU are commonly used activation functions that are more like softmax and stuff, but you can read up about them later. So let's go to the last layer now. So we've reduced the number of dimensions progressively and increased the number of filters. Now what we're going to do in this last layer is that since we have a 4 by 4, observe that this is also the same as our kernel size. So we'll take this kernel, put it on the one 4 by 4 image we get, and you get a 1 pixel output finally. Now we're almost done. We have 512 pixels. We using the flatten function, we convert that into one list, one dimensional array, and then we add them up. And we use the sigmoid function here finally, because all these values could be anything from 7, 5, 13, something. We take in all these real inputs and we convert them between 0 to 1. If you've not guessed, the reason why we do this is because what is a discriminator doing? It's giving us a probability between 0 and 1 whether our image is real or fake. So it is the sigmoid function helps us give a value between 0 and 1. So if it's 0, the discriminator is going to say that this is a fake image. And if it's a 1, the discriminator is going to say that it's a real image. So that is the architecture of the discriminator. Here we are loading the discriminator onto the GPU. Now, before we get to the generator, let's just look at one operation called transpose convolution. So just like in the discriminator, you had a bigger input entering that kept getting smaller and smaller and extracting features. What the generator is going to do is that we are going to give it a smaller input and we are going to use the weights to generate a bigger image. I'll show you what I mean. So yeah, this is the operation called a transpose convolution. So what we're going to do is we're going to take a small input 2 by 2, and after putting this single kernel, you're going to get a bigger output of 3 by 3. And it's a very similar operation. You can see how it takes, let's say 2. It operates on this 2. So 3 twos are 6, 2 ones are 2, 2 ones are 2, 2 fives are 10, and you get this upper half, upper quadrant, and then you do this for each of them, and then you just the overlapping guys, you just add them up. So 2 plus 12 is 14, 10 plus 4 is 10 plus 4 plus 0 plus 3 17, and so on, right? So this is very straightforward. And just like we had the convolution operation, we have this transpose convolution operation, and we start with a smaller dimension and we end with a larger dimension. So it's like the reverse of what's happening to generate the image. So once we see that, the generator architecture becomes pretty clear. Like last time, we started with 64 by 64 and we ended with that 1D array. Here we start with a 1D array called the latent vector. And this latent vector, the first time we load it in, is just going to be a random array. We're going to generate some random values and feed it to the generator. So it's going to start with a 1 cross 1, and using similar logic as the discriminator, it's going to increase it. So we start with 1 cross 1, then 4 by 4, 8 by 8, 16 by 16, 32 by 32. And finally, what we do is that we see that here there are 64 input channels. Here we force it to give us an output of 3, because these 3 represent RGB. And finally, we get our final function, our final image. Here the activation function we use is called the hyperbolic tan function. What that does is that it gives all the pixel values between -1 and 1. And if you ask why, there's the DC GAN paper that shows a lot of important reasons why we use our hyperbolic tan function to represent images, but that's what we do, and we get our final image. So discriminator, we given an image and we get you know probability, and for generator we give it a 1D array and we get an image. Now I'd like to give it back to Rohit to talk about the training of the generator discriminator and their iteration between them.
Ah, thank you, Aditya. So before directly jumping towards the code, what I will like to do is that explain you theoretical how the training loop will work and how we will train generator and discriminator. So I'm pretty sure that you understood till this point that in GAN there are two different modules. Uh, one is So in GAN we have two different modules. One is generator and another is discriminator. So first we will start with training of discriminator. Discriminator is nothing but a binary classifier, and it has two classes. One is real and another is fake. Um, so what we will do is that first we will give it a set of real images, and it will give out some predictions that whether the discriminator think that it is a real image or not. Uh, so as it is a real image, we want it to output one. So so the label for these kind of for when we are passing in the real images is one. So we will calculate the loss of loss real according to this. And then what we will do is that we will pass a set of fake images. Fake images means that it is generated by generator, and it will output some predictions again. And now as we know that it is a fake image, we want discriminator to predict zero. So now 0. Yeah. So we want it to give output 0. So according to this label, we will calculate the loss of fake images as being passed through discriminator, and we will call this loss as loss fake. So the final loss term for discriminator will be the sum of loss real plus loss fake. So and After calculating the loss, what we will do is that we will find the gradients according to this with respect to this loss function, and update the weights of discriminator in order to train. After completing the training of discriminator in round one, what we will do is that we will move towards the generator, and we will pass a latent vector into generator. Latent vector is nothing but a 1D array. We have made this notebook according to the original DC GAN paper, and in that they have used a latent vector of size 128, which means that it is an array of 128 into 1 into 1, and we pass it through generator, and it will output some image that will be of 3 into 64 into 64. And what we will do is that we will pass this image through discriminator, and it will give us some prediction. But in order to but what we want from generator is that it predicts it make out image it gives images which fool the discriminator to give a value of 1. So in order to calculate the loss function for generator, what we will do that we will make the label as 1, and we will find the loss function according to this label and the predictions made by discriminator. And after the calculation of this loss, we will call this loss as generator loss, and we will find the gradients of generator with respect to this loss, and update the weights of generator. After the training is done for generator, a single round of training is complete. We will run multiple rounds in similar fashion. First, discriminator, generator, until the set number of epochs are reached, and after that, we hopefully should get a uh, good image. And if still we couldn't find the image we are looking for, we can tune the hyperparameters, or we can try running it for a longer period. Now I think we can move towards the code. So yeah, this is a function which will display the images. Okay, yeah. First we will learn how we can train discriminator. This line of code, what it will do is that it will clear all the past gradients which we might have calculated for discriminator. After that, tells us that real preds will have the prediction made by discriminator when real images are passed. Real targets is equal to 1, as we know that we are passing real images right now. And then we will calculate the loss. In this For this notebook, we have used binary cross entropy. and this is what has been used in DCGAN paper. And we will give it two parameters. One will be the predictions made by the model, and another other real predictions. And on the base of this, the loss will be calculated. Then, after the real loss is calculated, we will move towards fake loss. And how we can do is that first we will generate a batch of fake images, passing the latent vector through generator. Then we will find the fake predictions by passing the fake images to discriminator, and then fake targets will be equal to zero, as we know that the image that these are fake images, and the discriminator a good discriminator should output zero in such case. And we will calculate the loss again in a similar fashion we did it for real loss, but the only thing different is that the here target value is zero, and the final loss will be real loss plus fake loss. These two steps are really important. These are back propagation. Loss or backward will calculate the gradients of all the weights in discriminator with respect to the loss function. Opt d will update the weights, yeah. After that, this is how we will generate a discriminator. After this, we can move towards training generator. uh, generator For generator, first we will create a batch of fake images, then we will pass it to discriminator, get predictions similar to what we did above. But the here only thing difference is that a target will be one, because we want generator to give such images that the discriminator gives an output of one. So by this thing we will force generator to produce images of such quality, so that we can get an so we can fool discriminator. After this, we will calculate the loss function for generator, predictions and targets. After this, we will again we will do the back propagation, loss backwards, and opt g step as we have done above. This is a function to save the samples in the ask directory. So right now, if I check, this is the kind of images a generator is giving. Okay. So now we have learned how we will train the generator and discriminator. Now this function, fit function, what it does is that it will keep the track of all the losses of G and D over the epochs, and it will run the training loop. So it will run for the number of epochs we give to this function, and the next for loop will load all lot. What it will do, it will load the batch of images one by one, and it will first call train discriminator function, which is above, and second it will call the train generator function. And after the end of one epoch, it will print all these values, the loss, real scores, and all of that stuff. uh, yes. And now what I'm going to do is that I am going to start the training. Yeah, so see, you can see that currently the one epoch is running. For this notebook, what I have done is that I have set the number of epochs as 100 and the learning rate as 0.0002. 100 epochs can take a lot of time, I say about 1 hour or something. So instead, I think we will share this code and the slide in the YouTube description, and you can run this on your own Kaggle accounts. But for now, I am directly going you to show the output, what kind of output we can expect. So here we can see that the images are quite good. Like, we can correctly identify all the eyes, hairs. We can and this is only what I have achieved after 10 epochs. So if you run this for complete 100 epochs, I'm damn sure that you will get a better quality image. The clarity will be better. But yeah, there's certain limitation to the kind of architecture we use. Over here we have implemented a simple DC GAN, and there are certain limitations to it. That what you can see is that over here the four continuous images are kind of similar. This is called mode collapse. uh, mm, Aditya, can you turn on the PPT? Aditya. And you can even see that the clarity is somewhat okayish. I've like you can totally see that there are some white lines, squarish white lines which are running over the images, and this is the problem with DC GAN in general, which have been solved by other architectures such as WGAN, uh, which solve most of the problem what DC GAN face. You can explore that, and I have even attached a playlist in the future exploration section, which you can access over there. Yeah. Yeah. So, beside the image generation, there are many hundred of different architecture for GANs. Some of them are updation on the DC GAN and does better than DC GAN, such as WGAN, and there are some GANs with a totally different purpose, such as SR GAN. What it does is that it creates a resolution of the input image. I guess in the original paper, what the authors did was that they converted a 512 image to a 2K image. That was a 4x upscaling. On the other side of the spectrum, we even have architecture like Cycle GAN. What, uh, what it does is that in the original paper, the authors converted a horse image to a zebra image. That what Cycle can do. And there are also pix to pix, and even you can guys can even explore style GAN. It was a one of the best GAN architecture designed by Nvidia. And at the end of the PPT, I have attached few resources for you guys. The first one is the YouTube playlist, which in this playlist the person has explained the theory, original paper, as well as code of five to six different kind of architecture. You can explore that. It is a really great resource. Second is the link of the original paper of GAN, and third is a Medium article which you can read. It has written everything in a really concise and a beginner friendly language. So thank you. I would like to thanks everyone for joining in, and I really hope that you guys have learned something really valuable, and you will explore this field even more. Uh, Thank you.
We would now like to ask any questions that the audience might have regarding our presentation. You could just enter it in the live chat.
Yeah. The reason why we use GPU is that it allows us parallel computation. Instead of what instead of running everything one by one, what it will do that it will update hundreds of weights parallelly. So it helps in that it reduces the time it need we need to training the model. Um, Image recognition. For image recognition, I guess CNN is good enough. We don't need to go towards the GAN. What GANs are really used for either image generation or for image transformation, like what they did in Cycle GAN. They convert a horse image to a zebra image. CUDA is basically it is a language to program GPUs and to program GPUs. So in this code, what CUDA represents is that represents the GPU. Like when can you switch over to the Kaggle the screen? So yeah, here here what CUDA represents is that it like in this function where I was doing toss.CUDA dot is available. It what it is doing is that it is CUDA represents the GPU. It is checking if the GPU is connected to my kernel or not, and if it is available to run the code. Uh, yeah, that's the that what is the significance of CUDA in at least in this code, and along and CUDA itself is a language which is used to program NVIDIA GPUs. Loss function. I would really suggest at this level you try to read papers instead of trying to make a loss function of yourself, because it requires very complex maths what function can use. Like if you're trying to implement wgan, I would highly suggest that refer to the original wgan what kind of loss function they have used instead of trying to choose on your own, because it can really make a big difference. And at this point I don't think so uh, I can tell you what is the mathematical reason behind that. It is all pure mathematics, not something CS related. Um, okay, guys, thank you. I really hope that you have learned something over here and you will explore the field of generative AI even more after that, after this session. Thank you.